Chapter 1 Patterns in Mathematics. Patterns we can see everywhere in nature, in our homes, schools, and the motion of the sun, moon, stars, etc. Mathematicians think of mathematics both as an art and as a science. Patterns in mathematics are predictable, repeating arrangements of numbers, shapes, or objects governed by specific rules. We can find out the next term that we can predict, and that is repeating arrangements. We can see arrangements of numbers, sometimes shapes or objects. It's all following some specific rules. So we can see there different types of patterns. There are number patterns and geometric patterns. Now we can look at that, how to identify the pattern. For that, first we have to observe. Look for trends, repeating cycles, difference between the nearest terms. And after that, analyze the rule. The rule which is connecting the terms like addition, division, multiplication, subtraction, etc. We can see the next term. To get the next term, some of this calculation work that we can apply. So find out how to apply and which calculation work we have to do to get the next term. That's that, analyze the rule. First we have to observe the trend, how it is going between the terms and or the difference between the terms. That way we have to observe and then analyze the rule. After that, predict and extend. Apply the identified rule to predict the next term or to complete the missing patterns or missing terms of the sequence. So this is the way first we have to identify the pattern and then we can find out the missing terms or the next term using the rule. We can see mathematics is useful everywhere. Here for example, the understanding of patterns in the motion of stars, planets and their satellites led humankind to develop the theory of gravitation, allowing us to launch our own satellites and send rockets to the moon and to Mars, etc. Similarly, understanding patterns in genomes has helped in diagnosing and curing diseases, to find out diseases in advance. For that also, that pattern is helping. So mathematics is very helpful everywhere. We can see different types of examples. Now first question in figure it out, page number 2. Can you think of the other examples where mathematics helps us in our everyday lives? Here we can see mathematics is not just an academic subject but a practical tool for navigating daily routines. Some examples are here according to the first question. First one, shopping and savings. To calculate unit price, discount, tax, best price, balance amount, to calculate how much we have to purchase. Everywhere maths is very we are using, very helpful. Another example, money management and budgeting. For tracking the expenses, calculating interest rates, handling credit, debit, transactions, etc. In bank or in scientific field, everywhere. All the workers are using mathematics in one or the other way. Another example, time management. Calculating travel time, speed, fuel consumption, etc. What time we will reach our destination, and everywhere we are calculating using the maths, calculating the time or speed of that vehicle or how much fuel we have to put in that, and GPS, etc. Another field is health. to calculate body mass index, heart rate, calories, pressure, etc. This is the way when we are looking, we can see mathematics is using everywhere. Mathematics helps us to make decisions, predict outcomes, and keep our lives in order. Second question, how has mathematics helped propel humanity forward? Here some examples are given. You might think for examples involving carrying out scientific experiments, running our economy and democracy, building bridges, houses or other complex structures, making TVs, mobile phones, computers, bicycles, trains, cars, planes, calendars, clocks, etc. So here the question, how has mathematics helped propel or to forward humanity, or helps the human beings to go forward, move forward? For that question we can write the answer. Mathematics has propelled humanity by economic development, eradication of diseases and increase in living standards, for designing infrastructure, computer technology, space travel mechanisms, coding, mobile devices, economic forecasting, banking, navigation, developing technology, etc. Here some examples are given in that question itself. So we can write these examples, or in the same page in the first paragraph there are also few examples are given for that question. How has mathematics helped propel humanity forward? For that the answer we can write from here, and we can use these terms and everywhere. From the technology side we can see same as that: designing infrastructure, computer technology, space travel mechanisms, coding, mobile devices, and also eradication of disease and increasing our standard of living and all the things. So these are few examples. Examples of number sequences. The branch of mathematics that studies patterns in whole numbers is called number theory. Number sequences are the most basic and among the most fascinating types of patterns. Here we can see how the numbers are repeating. First one, all ones. Next it is counting numbers 1, 2, 3, 4, etc. Here 1, then adding 2 with each one, starting with 1. Then 1 plus 2, 3, 3 plus 2, 5, like that way we will get odd numbers. Here starting with 2 and adding 2 to get the next number, 2 plus 2, 4, 4 plus 2, 6, etc. So these numbers are coming as even numbers. Then here 1, 3, 6, 10, 15, 21, 28, etc. These are triangular numbers, which means we can arrange these numbers in the form of a triangle. 1 is just 1 dot, 3 we can put it that in triangle form, 6 also the same way. That's why this sequence is called triangular numbers. Next one is 1, 4, 9, 16, etc. These are squares. We know that 1 square is equal to 1, 2 square is equal to 4, 3 square 9, 4 square 16, etc. Same way cubes. Next one, 1, 8, 27. This is 1 cube, 2 cube, 3 cube, 4 cube, etc. Next one is Virahanga numbers. That is another pattern. When we are adding two numbers, we will get the next one. 1 plus 2, 3. 2 plus 3, 5. 3 plus 5, 8. So when we are adding two numbers, if we are adding 5 and 8, 5 plus 8, that will be the next one, 13. Then 8 plus 13, that is equal to 21. So that particular sequence is called Virahanga numbers. Next one, 1, 2, 4, 8, 16, etc. These are powers of 2. First is 1, then 2. 2 we can write as 2 raised to 1. 1 we can write as 2 raised to 0. So the numbers 1, 2, 4, 8, 16, etc. is going on. 1 we can write as 2 raised to 0, 2 as 2 raised to 1, 4 is 2 square, 8 is 2 cube, 2 raised to 4, etc. So that means powers of 2. Here the number 1, 3, 9, 27, etc. Which one means same way powers of 3. 3 raised to 0, 3 raised to 1, 3 square, 3 cube, etc. So this sequence is called powers of 3. Figure it out, page number 3. First question, can you recognize the pattern in each of the sequences in table 1? Can you recognize the pattern of the sequence 1? We can see the first one, that is already explained. 1 is repeating. Second sequence, that is 1, 2, 3, adding 1 with the previous number. 1 plus 1, 2, 2 plus 1, 3, like that way. Next, third one, 1, 3, 5, odd numbers, adding 2, starting with 1 and adding 2. Even numbers, starting with 2, adding 2. Then triangular numbers. Here 1, 3, 6, 10, etc. It is coming, just add 2, 3, 4, 5, 6 with that number. 2 plus 1, 3, then 3 plus 3, 6. You have to add 2, 3, 4, 5, 6, 7, etc. with these numbers. Next one is squares. These numbers we can write as squares. 1 square, 2 square, 3 square, etc. 1, 8, 27, that we can write as in terms of cube. 1 cube, 2 cube, 3 cube, etc. Virahanga numbers, sum of two previous numbers. 1 as 1, then 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, 5 plus 8, 13, etc. Then powers of 2. 1 we can write as 2 raised to 0, 2 raised to 1, 2 square, etc. Last one, that is powers of 3. 3 raised to 0, 1, 3 raised to 1, 3. 3 square means 3 into 3, 9. 3 cube means 3 into 3 into 3, that is 27. 3 raised to 4. So powers of 3. Second question, rewrite each sequence of table 1 in your notebook and along with the next 3 numbers in each sequence. After each sequence, write in your own words what is the rule for forming the number of numbers in the sequence. So first one, we can see that is repeating 1, 1, etc. And then after that also it will continue like the same way. So here the rule is 1 is repeating. So next 3 numbers that also will come 1, 1, 1. Second sequence 1, 2, 3, 4. Here the rule is adding 1 with the previous number. So 7 plus 1, 8. 8 plus 1, 9. 9 plus 1, 10, etc. Next one 1, 3, 5. Rule is odd numbers adding 2. So 11 plus 2, 13. 13 plus 2, 15. 15 plus 2, 17. And then 19, etc. Next one, even numbers. They are also adding 2. After 14, 16, 18, 20, etc. Then triangular numbers. We have to add this the way the number. 21 plus 7 is equal to 28. So next we have to add 8 with that. After 28, 28 plus 8, it will come 36. Then we have to add 9 with that. 36 plus 9, 45. Then 10. 45 plus 10, 55. So it will go like that way. You have to add the numbers according to that. Next here, squares. Rule is squares of the numbers. 1 square, 2 square, 7 square is here. Next number is supposed to come 8 square. That means 64. Then 9 square, 81. And 10 square, that means 100. These are the next three numbers. After 49, 64, 81, 100. That means 8 square, 9 square, 10 square. Same way here cubes. Till 7 cube is 216. Next we have to write 8 cube, 9 cube and 10 cube. That means after 216, 8 cube. 8 cube is 8 into 8, 64. 64 into 8, 512. Then 9 cube. 9 into 9, 81. 81 into 9, 729. 10 cube, that is 1000, etc. Next, Virhanga numbers. Virhanga numbers means we have to add previous two numbers. 8 plus 13, 21. Next is 13 plus 21. 13 plus 21, it will come 34. Then 21 plus 34, it will come 55. And after that 34 plus 55, 89, etc. That means after 13 plus 21, then 21 plus 34. And then 34 plus 55, etc. These numbers are called Virhanga numbers. And rule is sum of two previous numbers. You have to add the previous two numbers to get the next term. Next sequence is 1, 2, 4, 8, 16, 32, 64, etc. That means powers of 2. 2 raised to 6 is 64. Now we have to find 2 raised to 7, 2 raised to 8, 2 raised to 9. So 64 into 2, 128. 128 into 2, it will come 256. Again into 2, 512, etc. Here these are the powers of 3. 3 raised to 0 is 1, 3 raised to 1 is 3, 3 square is 9, 3 cube is 27. So 4, 5, 6 like that. And next 3 numbers means 3 raised to 7, 3 raised to 8, 3 raised to 9. Now 3 raised to 7 means 3 raised to 6 into 3. 3 raised to 6 is 729. That into 3. So it will come 2000. Next number is 2187. Again multiply by 3. It will come 6561. Again multiply by 3 to get the next number, 19,683, etc. So powers of 3. These are the rules, and here the next 3 numbers of each sequence. Now visualizing these number sequences. Same table, this we can through pictures. To visualize that, we can see there on the next page. This is the pictorial representation of the number sequence from table 1. First one, it is all ones, just one dot. Next, counting number. So we had to add one dot. Here 1, next 2, 3, like that way, counting numbers. Next, odd numbers, 1, 3, 5, 7. Through dot we can represent that. Even numbers, same way. Next is triangular numbers. So triangular numbers, which means we can arrange these numbers in triangle form. 3, we can see this is the form of a triangle. If we join the outline like the same way, we will get a triangle. So these numbers are called, or this sequence is called triangular numbers. Next one, squares, that we can arrange in square form. 1, 4, 9, can see it's a square. So 1, 4, 9, 16, 25, etc. are called square numbers. Same way, next is cube. 1, 8, 27, 64, 125, etc. We can mark that as in the form of a cube. 125 small cubes are here. When we arrange, we will get a bigger one. These are the pictorial representation of the table 1 sequences, number sequence. Figure it out, page number 5. First question, copy the pictorial representation of the number sequences in table 2, this one, in your notebook. And draw the next picture for each sequence. Here we can see the first one, just continuing like the same way the numbers. So that one more dot it will come. Next one, here 5, and after that it will come 6. 1, 2, 3, 6 dots you have to mark it here. Here odd numbers. So after 9 is coming 11. But we can arrange it 11 dots in order. Next even number it is coming 12. So that also we can arrange it like the same way. Triangular number, next one it is coming after 15, 21. So we can arrange that in the form of a triangle shape. Then squares. Here 25. After the next number 6 square. 6 into 6, 36. So we can arrange that in the square form. Next last one, cubes. So that we after 125 it is coming 216. 6 cube. So that also we can arrange it with the pictorial representation like the same. Second question, why are 1, 3, 6, 10, 15, etc. are called triangular numbers? We know the answer that these numbers we can arrange in the form of triangle. So that is why it is called triangular numbers. Next, 1, 4, 9, 16, etc. are called square numbers. These numbers we can arrange in the form of a square. So that is why. Same way cubes that we can arrange in the form of a cube like the same way. These numbers. That's why it is called cube numbers. That we can write in sentence like the same way. 1, 3, 6, 10, 15, etc. are triangular numbers because these numbers of dots can be arranged to make an equilateral triangle. All three sides are equilateral triangle. Then next one, second one, 1, 4, 9, 16, etc. are square numbers because these number of dots can be arranged to make squares. Next one, like the same way. Next one, 1, 8, 27, 64, etc. are cube numbers because these many unit cubes can be arranged to make a bigger cube. Third question, you will have noticed that 36 is both a triangular number and a square number. That is, 36 dots can be arranged perfectly both in a triangle and in a square. Make pictures in your notebook illustrating this. So 36 we can write as the triangular number. This is the way, 36 dots. And at the same time 6 square is equal to 36. So 6 dots like that way, 6 rows and columns, it will come in the form of a square. 36 is a square number. So this is the pictorial representation. 36 as a triangular number and this 36 as a square number. Then next part, this shows that the same number can be represented differently and play different roles depending on the context. Try representing some other number pictorially in different ways. So some other examples are here. 1, 36, 1225 are triangular as well as square numbers. So we can see here number 1 that we can write as 1 is equal to 1 and 1 square is equal to 1. 36 already we proved here. Sum of all these numbers from 1 to 8 that is equal to 36. Next number 1225. If we are adding all the numbers from 1 to 49, we will get 1225. And also 35 square, 35 into 35 is equal to 1225. So these numbers are both triangular as well as square numbers. These are a few examples for that. Question number 4. What would you call the following sequence of numbers? 1, 7, 19, 37, etc. This is the hexagonal numbers, hexagonal shape. Draw this in your notebook. And what is the next number in the sequence? 1, 7, 19, 37. The next number we have to find out. Now look at the pattern, how the number is moving. And we have to find out the rule. How to find the next. By using that rule, we have to find the next term. Here the second term, that is 7. 7 we can write as first number plus 6 into 1. Third number we can write as second number 7, that plus 6 into 2. 6 into 2 means 12. 12 plus 7, 19. Hexagonal means the 6 sides. Next number. This third number plus 6 into 3. We will get 37. So the rule we can write as first number is same as that 1. Second number means the first number plus 6 into 1. First number is 1. So 1 plus 6, 7. Now third number means second number, that is 7. Then 6 into 2. 7 plus 12, 19. To get the fourth number, third number we have that as 19. That plus 6 into 3. Then the fifth number to get, fourth number is 37. 37 plus 6 into 4. So the next number is 61. Next number, we have to find the next number in the sequence, that is 61. So to get the next number, the previous number, that plus 6 into the previous fourth term, which term is here, that number we have to put. Fourth term, then 6 into 4. Third term, then 6 into 3. Second term, 6 into 2. First, second term, that means first number, that 6 into 1. To get the next one, the previous number, that plus 6 into the previous number, which term is that we have to multiply. Fifth question, can you think of pictorial ways to visualize the sequence of powers of 2 and powers of 3? First one, powers of 2. 1 dot, that means just 1, we can write in terms of 2. 2 raised to 0 is equal to 1. Then 2, that means 2 raised to 1, 2 dots. Next number is 4, which is equal to 2 square. So we can mark it like the same. Powers of 2, 2 raised to 0, 2 raised to 1, 2 square, then 2 cube. 2 cube means 8. Here in the cube we can see 8 dots. Next power is 2 raised to 4. That is 16. 2 into 2 into 2 into 2. 4 times, that's equal to 16. Here we can see 16 dots. See, it will continue like the same way. Similarly, powers of 3. Any number raised to 0 is equal to 1. So 3 raised to 0 is equal to 1. 1 dot. 3 raised to 1. That will come 3 dots in a triangle. Next power is 3 square, which means 9. So it will come 9 squares in this picture. Here the possible way of thinking about powers of 2. The shape is given here. Next is relations among number sequences. What happens when we start adding up odd numbers? 1, then 1 plus 3, 4, 1 plus 3 plus 5. Odd numbers is going 1, 3, 5, 7, 9, 11, etc. But here we are getting all square numbers. 1, 2 square, 3 square, 4 square, 5 square, 6 square, etc. Now, why does this happen? Do you think it will happen forever? So that we can write as each odd number can be represented as 2n minus 1. Because when we are multiplying any number with a 2, we will get even number. That minus 1, always that will be an odd number. When we add first n odd numbers, 1 plus 3 plus 5 plus etc. till 2n minus 1, we will get the answer as n square. So the same pattern is coming over here. This pattern will continue forever. Here the question, they will continue forever or not. So this pattern will continue forever. Sum of the odd numbers forming perfect squares. Here 1, then 1 plus 3, that means square of 2 or 2 square. Next is 3 square, 4 square, 5 square, 6 square, etc. So when we are adding, we can write in terms square of 1, square of 2, square of 3, square of 4, 5, 6, or in place of square of 2, that same thing we can write as 2 square, 3 square, etc. Now by drawing similar pattern, similar picture, can you say what is the sum of the first 10 odd numbers? We know that first 2n minus 1 numbers, that is n square. So first sum of first 10 odd numbers is equal to, which means 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Sum of all these odd numbers, that will be n square. Here n means 10 numbers. So sum, that will be 10 square, which is equal to 10 into 10, 100. Same way, next question. Now by imagining a similar picture or by drawing it partially as needed, can you say what is the sum of the first 100 odd numbers? 100 odd numbers means 100 terms. That will come over here. N square means 100 square. So 100 into 100, 10,000. Here another example of such relation between the sequence, adding up and down. Here we can see 1, 2, 3, 4. Till 4 it is going increasing order. Then after that 4 decreasing order. Adding up and then down. Last one here, the highest number 6. So 1, 2, 3, 4, 5, 6. Adding up. Going till that top and then coming back. 5, 4, 3, 2, 1. So this sequence, that is forming by adding up and down, up and down. Figure it out, page number 8. First question, can you find similar pictorial explanation for by adding counting numbers up and down? That means 1, then 1, 2, 1, 1, 2, 3, 2, 1 gives square numbers. Here we can see the number 1, then 1, 2, 1, then 1, 2, 3, going up, then down, 2, 1. Here till 4, 1, 2, 3, 4, then 3, 2, 1, going up and down. So we pictorial representation 1, here 4 numbers 1, 2, 1. 9 means 1 plus 2 plus 3, 1, 2, 3, then 2, 1. Here 16, 1, 2, 3, 4, then down, 3, 2, 1. So this is the way we can mark it. And that we can write as 1 square. This 4, 1 plus 2 plus 1, that is equal to 2 square. Next number, that is 3 square. So 1, 2, 3, 4, then 3, 2, 1. Sum of all this is equal to 16, that we can write as 4 square. So we can write in square number term. Second question, by imagining a large version of your picture or drawing it partially as needed, can you see what will be the value of 1 plus 2 plus 3 plus up to 100? Then going up and down, 99, 98, etc. up to 2 plus 1. That we can write as maximum 100. So that means n is equal to 100. Our rule is n square. So we can write 1, 2, 3, etc. up to 100 and coming down. So till 100, the highest number is 100. That means 100, that square. Our rule is n square. So n square, here n is equal to 100. So 100 square, which means 100 into 100 is equal to 10,000. So sum of all these terms is equal to 10,000. Third question, which sequence do you get when you start to add all the ones sequence up? What sequence do you get when you add all the ones sequence up and down? So two cases. First, if we are adding all the ones up, that means Counting numbers we will get 1, then 1 plus 1, that means 2, then again plus 1, 3, 1, 2, 3, etc. Counting numbers we will get. Here up and down. So 1, then 1 plus 1, then 1 plus 1 plus 1, like that way we have to arrange the terms, and we can find the numbers. There we are going to get the odd numbers sequence. This is the two cases. First we can take the sequence as all ones. So term 1, term 2, term 3, whatever the term, everywhere that will be 1. First term, second term, third term, everything that will be 1. The sequence is just 1, 1, 1. This is the sequence. So first case, adding the sequence up. When we are adding that, so first term is 1, second term also 1. When we are adding these two, 1 plus 1. 3 terms together when we are adding. 4 terms together when we are adding. So we are getting 1, 2, 3, 4, 5, etc. The counting numbers. So the first case, adding sequence up, that time we will get the counting numbers order this the way. Next is up and down. So first term 1 itself, then T1, T2, T1. First term, second term, then again the first term. But here everywhere that is 1. First, second, third, then second, first. Going up, then down. So here we are getting 5. Finally the answer we are getting 1, 3, 5, etc. That means sequence of odd numbers. Fourth question, which sequence do you get when you start to add the counting numbers up? Counting numbers upward. Can you give a small pictorial explanation? Here counting numbers we know that 1, 2, 3, 4, 5, etc. Adding counting numbers up, that means 1, then 1 plus 2, then 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, etc. So when we are adding, we are getting 1, 3, 6, 10, etc. Now we are getting the sequence of triangular numbers. So when we are adding counting numbers up, we will get triangular number sequence. And the pictorial representation of triangular numbers, it is coming 1, 3, like the same way, triangle shape. When we are adding, drawing the lines, we will get the triangle shape. So this is the pictorial representation of triangular numbers. Fifth question, what happens when you add up pairs of consecutive triangular numbers? Which sequence do you get? If you are adding triangular numbers, which sequence we are getting? Triangular numbers, here we can see 1, 3, 6, 10, 15, etc. Now already here we got in the previous question. And the required sequence, that means if we are adding the numbers 1 plus 3, then 3 plus 6, 6 plus 10, etc. When we are adding, we are getting 1 plus 3, that is 4, 3 plus 6, 9, 6 plus 10, 16, 10 plus 15, 25, etc. Now we can see these numbers are the square numbers. So we can write as 2 square, 3 square, 4 square, 5 square, etc. Sequence of square numbers. So see, square numbers pictorial representation, we know that they are on the page number 4, the previous table. Here is the pictorial representation of square numbers. Question number 6. What happens when you start to add up powers of 2? Starting with 1. Take 1, then 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8, etc. Now add 1 to each of these numbers. What numbers do you get? Why does this happen? Here powers of 2, that means 2 raised to 0, 2 raised to 1, 2 square, 2 cube, etc. These are the numbers, means 2 raised to 0 is 1, 2 raised to 1, 2, 2 square is 4, 8, 16. These are the numbers. So when we are taking these numbers, we are getting 1, 1 plus 2, 3, 7, 15, 31, etc. And when we are adding 1 with that is the question. If we are adding 1 with these numbers, what we will get? So then we will get 2, 4, 8, 16, 32, etc. That means in terms of power of 2. Each and every number we can write in terms of power of 2. Then why it happens like that way? We know the rule in general 1 plus 2 plus 4 plus etc. up to 2 raised to n is equal to sum of these numbers is equal to 2 raised to n plus 1 minus 1. This is the general rule. When we are moving this minus 1 to the left side, that will come plus 1. That means this one. Minus 1, when we are moving to the left side of the equal to sign, that will come 1 plus the entire thing, which is equal to now remaining on the right side 2 raised to n plus 1. So we can see here 1 plus the power of 2, that is equal to 2 raised to n plus 1. That means 1 plus this 2 raised to 0 plus 2 raised to 1 plus 2 square plus etc. plus 2 raised to n is equal to 2 raised to n plus 1. Here we can see there in the example. This one is 2 raised to 0. 2 raised to 1, 2 square, 2 cube plus 2 raised to 4. That we are getting as 31. When we are adding up to 2 raised to 4, we are getting 31. That plus 1, this 1. So 32. The power is here 5. If the power is here 4, that plus 1. So 2 raised to 5. Here 8 is 2 raised to 3. The highest power. When we are adding the terms, here the power is 3. And that plus 1, that means 16. So it will come 2 raised to 4. So whatever the power of this term, this sequence, the last one, that plus 1 will be the sum of that answer. Power of 2, 2 raised to n plus 1. In general, if you are taking n as the power of the term, last term, then it will come 2 raised to n plus 1. Here it is 4, then 4 plus 1, 5. Here it is 3, then it will come 3 plus 1, 4. 2 raised to 4, 2 raised to 5, etc. Question number 7. What happens when you multiply the triangular numbers by 6 and add 1? Which sequence do you get? Can you explain it with a picture? So when we are doing any addition multiplication, we will get another sequence or another pattern. Here we are going to multiply the triangular numbers by 6 and add 1. We know that triangular numbers are 1, 3, 6, 10, 15, etc. Multiply that number by 6 and add 1. So first number is 1. 1 into 6 plus 1 is equal to 7. Second number 3. 3 into 6 plus 1, 19. Third number 6. 6 into 6 plus 1, 37. Next number 10. 10 into 6 plus 1, 61. Next is 15. 15 into 6 plus 1, 91. So now we are getting 7, 19, 37, 61, 91, etc. What type of sequence is that? This is the hexagonal number sequence. Sequence of hexagonal numbers. The pictorial representation that we can see in page number 5. Here is the hexagonal shape. 1, 7, 19, 37, etc. So the same numbers what we are getting here. 1, first one 1, then 7, 19, 37, etc. The hexagonal representation. 8th question. What happens when you start to add up hexagonal numbers? So hexagonal numbers 1, 7, 19, 37, etc. If you add that 1 plus 7, 8. 1 plus 7 plus 19, 27. 1 plus 7 plus 19 plus 37, 64. So now we can see these numbers. 8, that is 2 cube. 27, 3 cube. 64, 4 cube. So when we are adding the hexagonal numbers, we are getting the new sequence as 1 cube, 2 cube, 3 cube, 4 cube, etc. This is the sequence of cube numbers. So the picture of pictorial representation of that. And question, find your own patterns or relations in and among the sequences in table 1. Can you explain why they happen and with a picture or otherwise? In table 1, we can see different patterns, and we already noticed that if we are adding or continuing with a particular rule, we will get another sequence. From that, if we are taking 5, 10, 15, 20, etc., it will come multiples of 5. Another example, 4, 8, 12, etc. First number is 4 and add 4 with that. Then we will get a sequence or multiple of 4. Same way with any number. So we can find different sequences from the numbers system. Now patterns in shapes. Examples of shape sequences or patterns in shapes. First pattern, here we can see 3 sides. With the 3 sides, we are getting a triangle. 4 side quadrilateral, 5 side pentagon, 6 side hexagon, 7 sided picture heptagon, 8 sided octagon, 9 sided nonagon, 10 sided decagon. So regular polygon. Regular polygon means all sides are in the equal length. All sides are equal in length. So these all 3 sides are equal in length, which means that triangle is equilateral triangle. Quadrilateral, 4 sided with equal length, that it will come square. When all 5 sides are equal in length, so regular pentagon. This is a regular hexagon. So this is that one of the example shape sequence. Another one here, in between 2 dots, number of lines we can write the sequence here, 1. Between 3 dots or in this shape triangle, not between 3 dots, in this triangle shape we can see 3 sides or 3 line segments, number of lines 3. In this picture 1, 2, 3, 4 and diagonals 5, 6. So total 6 lines are there, line segments are there. Here 10, next is 15. So it is going on that graph like that way. Same way, next is small number of squares. If you are counting here 1, only the small squares, number of small squares. 1, 2, 3, 4. Here 9, 16, 25. So stacked squares inside that small squares. Same way, next one, number of small triangles. 1, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 25, etc. So stacked triangles, small triangles. Again the last one, number of sides. In that picture we can see it's a coach snowflake. 3 sides, then 12 sides, 48 side, 192, 768, etc. Snowflake, coach snowflake, that means it's multiplying by the number. Look at here, 4 into here 3 sides. So 4 into the previous number. 4 into 3, 12. 4 into 12, 48. 4 into 48, 192. 4 into 192, that will be 768. So that pattern is going like that way. Figure it out, page number 11. First question, can you recognize the pattern in each of the sequence in table 3? First one is regular polygons. Number of sides increases by 1. Here 3, 4, 5, 6, 7, 8, 9, 10, etc. So number of sides increase by 1 at a time. Triangle, quadrilateral, pentagon, hexagon, etc. So the sequence formed, that is 3, 4 with the line segments 3, 4, 5, 6, etc. Second case here, number of lines K1, K2, K3, K4 it is given. So K2, the first figure with 1, second figure with 3, 6, etc. So the sequence formed is 1, 3, 6, 10, 15, etc. Next one, the square formed in this. The square formed, that is 1, 4, 9, 16, 25, etc. That sequence is called square number sequence. And next one, 1, 4, 9, 16, etc. So that is power of 2. So number of small triangles that we can write as 1, 4, 9, 16, 25, etc. This we can write as 1 square, 2 square, 3 square, 4 square, etc. So this sequence formed as 1, 4, 9, 16, 25, etc. And that is a square number sequence. The last one, 3, 12, 48, 192, etc. That is formed by 3, then 4 into previous number, 4 into 3, 4 into 12, 4 into 48, 4 into 192, etc. So we can write like this way. The sequence formed is 3, 12, 48, 192, 768, etc. Relation to number sequences. Here we can see the counting numbers 3, 4, 5, 6, etc. in each shape, regular polygons. So regular triangle, quadrilateral, according to the side number of sides, the name it will change. Triangle, that is equilateral triangle, then square, etc. Regular, pentagon, hexagon. So the term, the word regular, which means they have equal length of sides. So these shapes have equal length sides and also equal angles. Figure it out, page number 11. First question, count the number of sides in each shape in the sequence of regular polygons. Which number sequence do you get? What about the number of corners in each shape in the sequence of regular polygons? Do you get the same number sequence? Can you explain why this happens? In the regular polygon, number of sides equal to number of vertices. 6 sides, which means 6 vertices. 10 sides and 10 vertices. So we can write, in a regular polygon, number of sides is equal to number of vertices. First one, equilateral triangle. So in equilateral triangle, number of sides 3, number of vertices also same 3. Next one, square. Number of sides 4 and vertices also, number of vertices also 4. Same way, whatever the shape in the regular polygon, number of sides is equal to number of vertices. Second question, count the number of lines in each shape in the sequence complete graphs. Which number sequence do you get and can you explain why? Here the sequence we can see, that is 1, 3, 6, 10, 15, etc. So we can write the sequence first. We get the sequence 1, 3, 6, 10, 15, etc. That means number of lines. This is the triangular sequence, triangular number sequence. Third question, how many little squares are there in each shape of the sequence of stacked squares? Which number sequence does this give? Can you explain why? Now here we can see this is the stacked squares, the number of small squares, that is coming 1, 4, 9, 16, 25, etc. So we can write that the sequence 1, 4, 9, 16, 25, etc. And this is the sequence of square numbers. Fourth question, how many little triangles are there in each shape of the sequence of the stacked triangles? Which number sequence does this give? Can you explain why? Here in triangle shape, this one. Here number of small triangles, that is given as 1, 4, 9, 16, 25, etc. So we can see how it is forming that first the sequence. We get the sequence that is 1, 4, 9, 16, 25, etc. This is the sequence of square numbers. And by adding a stacked triangle at the bottom, the next number of the sequence, that means the square number that we will get. Fifth question, to get from one shape to the next shape in the Koch snowflake sequence. 1. Replace each line segment by speed bump. That's 1. So we can see that coach snowflake, which means one line segment, we are making that into 4 parts. 1, 2, 3, 4 parts, or 3 divisions we have to make it, and make that in bump shape or this shape. Then we will get the next one. So each side, when we are doing the same way, we will get the nest shape. So how many total line segment are there in each shape? Here we can see coach snowflake starting with triangle 3 sides. Each side we have to divide that into 4 parts and make a speed bump like the same way. We will get the nest shape. That's why we are multiplying this number of line segments that with 4 to get the next one. Again, each side, each line segment we have to divide into 4 equal parts, and the middle 2, just it will come up the bump shape. Then the next one it will come. So we get the sequence 3, 12, 48, 192, etc. First term is 3. Then each one multiply with the 4. 3 into 4. Then the answer is 12. That 12 into 4, 48. 48 into 4. Like that it is going. So the previous term, that into 4, then we will get the next term. One straight line in the beginning that we are making into 4 equal parts, and the second and third portion or the middle 2 portions we had to make it up like the same way. So one line making into 4 equal parts. So 4 sides, 1, 2, 3, 4 sides. Multiply that one with the 4, we will get the next one. So 12, 12 into 4, 48. Like that way the sequence is forming. Now, how many total line segments are there in each shape of the coach snowflake? Here it is given, that is 3, 12, 48, etc. So 3, 12, 48, 192, 768, etc. We already noticed that. Now that is 3 times of powers of 4. Yes, we can write that powers of 4. 3 times of 4, 3 into power of 4. 3 into 4 raised to 0, that means 3 into 1 is equal to 3 itself, first number. Then 3 into 4, 12. 3 into 4 square, 4 square is 16. 16 into 3, 48. Then 3 into 4 cube. 4 cube is 4 into 4, 16. 16 into 4, 64. That into 3, 192. Again, 4 raised to 4, that into 3, we will get 768. So this is the number of total line segments in each shape of coach snowflake, and that we can write as 3 times power of 4 in that form.